What's good? Today we're going to talk about how to use script files in MATLAB. Let's get right into the content and start thinking about why we might want to use MATLAB script files. As a case study, we're going to look back at a very classic problem that shows up in many math classes to kind of make a point about using MATLAB. That problem reads, please solve the quadratic equation 2x squared minus 5x minus 3 equals 0. And what we mean by that is to find the value or values, there might be two of them, of x that makes this equation true. For example, a solution to this equation is definitely not 0, since 0 squared is 0, 2 times 0 is 0, minus 5 times 0, so 0 minus 0 is 0, and then 0 minus 3 is negative 3. Negative 3 is definitely not equal to 0, thus, because the value x equals 0 makes this equation false, we say that 0 is not a solution. This problem is asking us to find the values of x that make this equal sign true. In other words, the input values of x that turn the left-hand side to 0. Some mathematicians call this find the 0 of that quadratic equation or find the roots. Classic problem in mathematics. In order to motivate why we're going to use script files, we're going to study trying to solve this problem in MATLAB. One of my best practices for encouraging deep thought in scientific computation is to actually spend time thinking deeply about a problem before we write any lines of code. In other words, when trying to leverage MATLAB or any computer language, before we sit down to actually write code up, I would encourage you to really think about what the problem is asking and how we might leverage our software to make progress towards solving that problem. With that best practice in mind, the practice of understanding a problem before we open our software, let's do some recall from our previous lives in mathematics. Remember, we had this thing called the standard form of a quadratic equation. That's a nerdy way to say we can categorize the format, the anatomy of this equation using this general form. ax squared plus bx plus c equals 0. If we compare the general form with coefficients or scalars a, b, and c with the specific equation that we're trying to solve, in this case, we see this correspondence. We have 2x squared plus negative 5x plus negative 3 equals 0. We continue our journey into the past by remembering that we can actually identify the specific values for each of those coefficients in standard form. Here we see that a is equal to 2, b is negative 5, b is the coefficient in front of the x term, here I have negative 5, a is the coefficient in front of the x squared term, here I had 2. And then c is negative 3. So we've now specifically identified the value of the scalars in the general form for this specific example. Assuming we felt enough pain in our previous lives in mathematics, we probably have a few different tools in our toolbox to solve this equation and produce the values of x that we want. One of those we could call the AC method. If you want more information about the AC method, I'll link in a YouTube card on the top right-hand corner of this video to other videos that I've made to address that method. We also have something called complete the square, which is really the source of information for the quadratic formula. That quadratic formula is yet a third algebraic technique that we can use to solve this equation. And then we also have something called a graphical solution, which I'll also link to a video now. In our case, we want to study how to use MATLAB to solve this problem. I'm going to go ahead and suggest that let's use method 3, which is the quadratic formula, since it's the one that produces a closed form equation that allows us to solve this quite quickly. The quadratic formula states that if we have a quadratic equation in standard form, ax squared plus bx plus c equal to 0, then we have two possible solutions that take this form. The first solution, or the x coordinate of the left point of intersection between our parabola and the y equals 0 line, in other words, the x-intercepts of this parabola, that x coordinate is given by negative b minus the square root of b squared minus 4ac all divided by 2a. The x coordinate of a possible right point of intersect between the parabola and the x-axis is negative b plus square root of b squared minus 4ac divided by 2a. There were three different cases that we had. The parabola could intersect twice, having two different points of intersection. The vertex of the parabola could be on the y equals 0 line or the x-axis, or the vertex could be above while the parabola points up, or below while the parabola points down. Those are both what we call complex roots or complex solutions to that quadratic equation. Hopefully this is a review. If not, you can look back at some of my previous videos from different classes to get your head around what I'm saying here. The point of this is we are kind of ready, I suppose, to boot up MATLAB and start calculating solutions to our specific problem using the fact that we've identified the values of the coefficients A, B, and C, and we have a closed form formula that we want to use MATLAB to calculate. I do want to note that this is not quite an authentic representation of the type of work that needs to be done to start coding on a scientific computation problem. Here I'm making a big assumption that many of my viewers will have seen the approach to solving quadratic equations using the quadratic formula. So this is just a kind of a recall. Oftentimes when we're actually coding solutions to scientific computation problems, studying the problem takes a significant investment of time and energy, maybe on the order of days, weeks, months, or even years. Nonetheless, this reinforces the point. A best practice in using MATLAB to solve problems is to study the problem in detail and document your understanding of the problem prior to writing code so that there's a relationship between the code that you write and your understanding of what you're trying to do behind the scenes. Here we are in the MATLAB command window. We see that the cursor is right next to the command prompt. The goal of this particular coding session is to solve the quadratic equation 2x squared minus 5x minus 3 equals 0. We have the approach that we want to implement, which is to use the quadratic formula. In order to do this, we see that we need to declare some variables. First, we need to say that a is equal to 2, and we'll store that. Then we say b is equal to negative 5, and we store that. And c, in this case, we saw was negative 3. Then we have this thing that said x1 was negative b minus, and I think we call this the square root function of b squared minus 4 times a times c. And then the entire thing, well, you know, I didn't do a great job on this. Let me go ahead and just copy and paste inside the parentheses. And on the bottom, I'm going to go ahead and write parentheses again and then type 2 times a. So that will be root number 1. Let's go ahead and enter that. In this case, it's claiming that my x1 value is negative 0.5 or negative 1/2. Let's try x2, which was basically the same line of code. In this case, I'm going to push the up arrow so that I can get to the last command. I love reusing code whenever possible. Let's change the 1 in this variable name to 2 so that I know that this is the second x that I'm looking for. The only difference between my first root and my second root is the negative in front of the square root turns to a positive, and that goes to the famous negative b plus or minus the square root of blah, blah, blah. Here, let's go ahead and run this and see what the values are. Of course, one of the things that is true in scientific computation is we want to check to see if our guess solution, if the solution that we are proposing is an actual solution. To do that, notice that we could say a times x1 squared plus b times x plus c. Oh, this should be x1. Let's go ahead and see what that value is. It should be 0 if x1 is a solution. Indeed, the value is 0. We now feel confident that MATLAB has produced the first solution that we were looking for. Let's take the second solution. In that case, it's the same check, except instead of variable x1, we're going to use variable x2. If the x2 value that I produced, which is 3, is indeed a solution to this problem, the output value of this expression should be 0. Let's go ahead and enter that command and execute it. Notice I have now found 2 different roots of my original quadratic equation, 2x squared minus 5x minus 3 equals 0, and those roots are negative 1/2 and 3. We've confirmed that in MATLAB. We're feeling pretty good about ourselves. You might be wondering, hey, I thought this video was about script files. When are we going to get to that? We're working on it. The reason that I want to focus on coding in the command window to start with is to show you some of the strengths and weaknesses of command window programming so that we can highlight why script files are useful as we build our first script file to solve this problem. To do that, let's go ahead and look here. As we code in the command window, we're using MATLAB as an interactive terminal language where we process a single line of code and then immediately output the results of that line. Go on to the next line. We process the next line of code, produce the results, the next line of code, produce the results. And as we move down, MATLAB has access to results from previous executions step by step. We call this sequential execution because we started with step 1, then we went to step 2, produced the output, single lines of code produced individually. This is really nice for back of the envelope calculations and getting a quick response from MATLAB for specific questions that we might have that don't take a lot of work. However, if we try to write code that solves multiple problems at the same time and then test that code, the command window format very, very quickly becomes cumbersome. Let's take a look at why that might be true. Suppose our original problem was not only to solve the quadratic equation that we started with, but also to solve general quadratic equations that might take different form. In other words, we want to produce an algorithm, some sort of a script for solving any type of quadratic equation that we might encounter in our classes. Of course, we've seen using the command history window, we can reuse old code. So here I'm declaring the variable a equal 2. Perhaps I use my problem down here. Let's look at problem A and the extended version, and we'll say that a is actually 3. We'll go ahead and recopy b equals, looks like perhaps 1. And then we have c equals -4. Then we take x1 and calculate that, and x2 and calculate that. Now we're reusing all that code. So the claim is if I've done my entry correctly, the solutions to my original equation should look something like this. Let's go ahead and calculate that out. We'll type in this is 3, this is 1, and that is 4. Should be 0. Wait a second, it's not 0, it's 6. Well, what happened there? Oh, looks like, actually I did this on purpose, b should not be -1, it should be +1. So let's go ahead and rerun that thing. So this should be +1. And then let's go ahead and check that. Still getting 6. Oh, that's because I need to rerun x1. So now I go back into x1, I run it again, I go ahead and check. Now it's 8. Oh, something's not, oh, I see. This should be a negative. Are you noticing how frustrating this is to correct little errors? Every time I go through the process of correcting these errors, this was an error. Notice it should be a negative based on what we see over here. But the point of the matter is that now I have to actually go in there, put a negative in, rerun it, and I now checked my work. Because this is a single line interpretive language, every time I'm running new code, I have to run the sequence if I expect it to work well. Another way to say this is that the command window is not really designed for larger programming projects. It's more designed for back of the envelope calculations and to put us in command of many other operations that we might want to do in MATLAB. One alternative approach to deal with some of the weaknesses of the command window is to make what we call a script file. If you go up over here to the Home tab in this tool strip, the File section of the tool strip, let's go ahead and click on the New Script button. The moment I click on the New Script button, MATLAB opens a script file in the editor browser. This is a new browser that we have yet to see. It is designed for writing and editing script and function and class files in MATLAB. Along with our new editor window where we're going to write our script file, we also see some new tabs along the tool strip here. Originally we had only 3 tabs, the Home, Plots, and Apps tabs. Once we open the editor, we actually see 3 new tabs, which are the Editor tabs, the Publish tab, and the View tab. These tabs provide point and click access to many popular tools that we might want to use when writing code in a script file. We're going to stay on the editor tab for now. Here is the code that we're looking at. Let's go ahead and copy and paste our previous code into our script file from the command history. So literally all I did is I just copied and paste. Before we do anything else, let's make sure to save this. One feature that I want to call out: when we clicked on the new script file, MATLAB automatically created a script file which was called untitled. In this case, it's untitled 2 because I had opened 2 script files in this session. right next to the title, do you see that little asterisk or star in the superscript? That is an indication to me as a coder that I have made changes in this script file that I have not yet saved. In other words, this is an indicator that gives me a warning that I could lose code that I've written unless I save it. Here we're going to use the save button. So we'll go down to save as, and we will navigate our system's hierarchy. By default, MATLAB will store script files, or what we call .m files, in the MATLAB folder. We could store this here. I'm going to go ahead and navigate to my desktop and call this what we say quadratic equation solver. And maybe I do Jeff's quadratic equation solver. I'm going to start my file with a capital. And that is because MATLAB starts all of its native built-in functions with a lowercase. This is a good habit to let me know this file is something that I wrote as a user, not something that is built into the MATLAB environment. Let's go ahead and save this file. Notice in the editor, I now have the path to that file as well as the file name. In other words, in my hierarchy, I'm going to go to the users folder. Then I'm going to go to Jeff's subfolder, then the desktop directory. Then I'll find in that desktop directory, I'll find the file Jeff's quadratic equation solver.m. When you see .m, that is a MATLAB file type that stores either script files like the one we're writing here, or function files, which we'll see in later videos. Notice the asterisk here is gone, but if I were to change, let's say the C value to 1, because I haven't saved that, the asterisk reappears. And if for whatever reason I quit MATLAB or my operating system force quit MATLAB for some reason, I would lose that bit of code. The way to avoid this is to save frequently. Now that I have this save, I can run all of this code by pushing a single button in my run section of the tool strip associated with the editor tab. Let's go ahead and do this. We'll run. MATLAB comes up with a statement that says, in order to run this, you need to make sure that you are in the folder where that .m file sits. Notice that right now, the current folder that MATLAB is searching is the default folder where I open MATLAB. Specifically, it's in users, then I go to the directory Jeff, then documents, then MATLAB. In other words, if I go to Jeff, then it looks like documents, then it looks like MATLAB. Basically, MATLAB is going to be looking for this script that I've written, Jeff's quadratic equation solver, in this folder. However, we notice at the top in the editor window, the file that I want to run is not in this directory. It's actually in Jeff, then I go to desktop, and lo and behold, there's the actual script file. What MATLAB is telling me when I go to run this is, in order to run this script file, please tell me where to find it. By default, I'm going to search in the current folder where my pointer is located. Here, if I push change folder, we can get to that space, and immediately the working path of MATLAB is now identical to the location where I've stored this file. Don't worry about any of that. Just click the change folder button. Later in our work together, we'll talk about the current folder, set paths, and all the beautiful things that MATLAB does to leverage code in different places on our computer. For now, notice that our script file actually executed the sequence of commands in order. I can see that because this title shows up, which says I've run that script file, and then each of these commands run separately. So first we highlighted that A equals 2, then B equals -5, then C equals -3. Then we executed both of these lines of code. Then we did the check. Do you notice the difference there between command window coding and script coding? Here I've executed an entire block of code sequentially. First the line 1, then line 2, line 3, all the way down by clicking a single button. In other words, this is a super sleek way to do a bunch of work with one button. Moreover, there's some kind of nice features to this. Notice that the equal signs are highlighted. If I take my cursor and scroll over the equal sign, MATLAB is telling me if you terminate this statement with a semicolon, we can suppress the output. Let's go ahead and do that for the first few. So A, B, and C. Notice that those highlights to the equal signs or assignment operators disappear. If I now rerun that code, the A, B, and C output in my second execution have disappeared. In fact, I can suppress all output in this situation. If I now save my script file and then run it, let's go back to the command window. Let's go ahead and clear the command window. And then notice we could run our script file by pushing this button. But another thing that we can do is we can actually type the name of the script file in the command window. So the name of the script file is Jeff's Quadratic Equation Solver. So let's go ahead and put J, and then I'm going to push Tab. Notice MATLAB will tell me here are some things in my system that start with J. In this case, this is the one that I want. So I double click it, and then I push Enter. MATLAB produced no data for me. Didn't print out anything to the command window, even though in my workspace, those variables are saved. Let's see that again. Let's go ahead and clear the command window. And then here we'll clear the workspace. So MATLAB has no variables stored in the workspace. Let's run our quadratic equation solver again. There I just type in Jeff, I push Tab. MATLAB automatically filled in anything that starts with Jeff and gave me choices. In this case, there's only one file in the entire MATLAB library that starts with that. It's my script file. When I push Enter, MATLAB now runs all of this code sequentially, and it stores those pieces of information in the workspace. I do want to call this out. Notice that the last two lines of code are not assigned to a particular variable, and by default, MATLAB stores that in answer. These two lines of code are designed to check our work. First, we're checking with X1, then we're checking with X2. We might decide to call this check 1, and we'll call the second check check 2. Let's save what we've done. We'll go ahead and clear our memory and clear the command window. Let's go back and run Jeff's Quadratic Equation Solver. In this case, I'll just double click on it. Now I can actually check 1. The line of code that I propose solves my quadratic equation actually does produce a 0 when I check it with the original equation. So too, I can see check 2 also solves my equation, and I have the two values stored. Here is my first solution, which is the left point of intersection with the x-axis. It's -1/2. Here's my second solution, 3. Now I have a script. I have a general format, a general program that allows me to solve any quadratic equation that I might want. Specifically, let's take a look at problem A of our extension problem, which said that in this case, A was 3, B is 1, and C is -4. We'll go ahead and solve that. We'll rerun this script. Notice I can solve that quadratic equation quite quickly. And in fact, MATLAB has told me that the left solution is -1.3333. I'm guessing that's -4 divided by 3. And then the other solution is x2 equal to 1. Both checks of this code work out. One thing that I might do is actually associated the check with the code right next to the actual line, which means I can rearrange this and then they're executed sequentially in memory. Let's go ahead and see what happens if I rerun that code. Indeed, we get what we want. We see here that it looks like in the workspace, the variables that we declared are ordered in lexicographical order. In other words, A, B, C, D, E, F, G. In that order, I can see all the variables that I have as well as their values, which we've seen in previous videos. One feature of the editor window that I want to call out are these numbers along the left-hand side, 1, 2, 3, all the way down. Those are line numbers. In other words, this allows me to refer to specific lines of code. So for example, if I said, viewers, please take a look at line 5, we could immediately go down to line 5 and see what that code reads. And this is super useful to be able to debug code and then break code into sections. Another thing that I can do in my editor window is actually undock this, which allows me to think about editing MATLAB code using the entire screen, which is kind of useful. Of course, we could also redock this by just putting dock the editor. That concludes our first introduction to script files. We are not at all done with this problem. This is what I would call very poorly written code. There's no title information, there's no help documentation, there's no author information, and there's not extensive commenting. Those are all features that we're going to include in the code that we write. The point of this video was to highlight some of the power behind script files when we compare that to what we do in the command window. One final thought I want to leave with you is an analogy I like to use on how to think about the command window versus script files. The command window is designed for line-by-line execution. In other words, I type a single line of code and MATLAB produces a single output associated with that, all done sequentially. Script files, on the other hand, allow me to batch code together and run all the code from the first to the last as a single unit. This reminds me of English class. Command windows would be like pieces of paper and pencil where I'm jotting down ideas for an essay that I'm trying to write. Oftentimes when I'm writing an essay, that happens over a period of weeks, and ideas might come to me when I'm not on my computer. So what I do is I just jot those down on a piece of paper. That's off the cuff scratch work that will help me when I actually sit down to type. However, when I get ready to write my essay to submit it, usually I'm going to boot up a software on my computer, maybe like Microsoft Office or TextEdit, where I can type my essay in a reusable format that I can edit, revise, delete, make changes to very, very easily. That is what I would call a script file. The command window is great for off-the-cuff calculations with short ideas that I'm trying to get a sense of. Script files allow me to solve much larger problems by allowing revisable code and editing functionality. That leads us into our challenge for today. For you viewers at home, in the comments section on this video, please write your own analogy for describing the difference between the command window and script files. What ideas do you have about describing how those are different in MATLAB? I also welcome your questions and feedback. I become a better content creator when I get your feedback. You all have such great ideas and wonderful thoughts. It's super useful for me to hear about those. Hopefully this gives you some sense of how you can leverage script files. In a future video, we're going to talk about how to format those properly to make this readable. I'll see you soon.